Now let us look at a different arrangement of resistors. This is called resistors in parallel. So this is shown in the circuit diagram here in this slide. And you can see that again, we assume that the internal resistance of the battery is 0. The battery provides a voltage delta V, and there is a current I flowing in the circuit. And there are two resistances, R1 and R2. The important point is to note that these are now connected in parallel. So the current I is coming to point A, and this current now has two paths to flow through R1, either through R1 or through R2. So the current actually gets divided into two components, I1 and I2, and these currents flow through each of the resistors, and then they meet at point B and recombine as the current I in the circuit. So, and also notice that the potential difference between points A and B is now just the potential voltage delta V provided by the battery, because these are just the terminals of the battery. And so R1 and R2 has the same potential difference now. So when two resistances are connected in parallel, they have the same potential difference. The currents flowing through them can be different if they are if the magnitude of the resistances are different. But the point is that, like, the current again adds up. The current basically at one point gets divided into components, and then it recombines basically. So in parallel, each device operates independently of the others, right? So if you break one of the current paths, the other device still works, right? So if you break the circuit, if you break the current flow for R1, then R2, the current can still flow through R2. So R2 still is working in the circuit. So also, because the current gets divided into the various paths, the lower resistance will have the higher currents, right? Because the potential difference across all the resistances will be the same, and we know V equals IR. So if the resistance is higher, then current will be lower, and if the resistance is low, then the current will be high. Also, even if the resistances are very high, they will have some currents flowing through them in this configuration. So here is an example, again the same example. Also in this case, you can define an equivalent circuit an equivalent resistance for the parallel configuration of the resistances R1 and R2. We will show how to do this. So this has the parallel configurations also have an important implication. So in most of the devices that are in households, they are all connected in parallel basically. That's because you can switch off one without switching off the other, right? If they were all connected in series, if you were to switch off one, all the other devices would be switched off because it's the same current flowing through all of them. But now the currents are divided, they are flowing for different paths. You can switch one of the devices off and still have the other device on. So parallel configuration is used in most of the electrical equipments and household circuits, basically in household circuits. Circuit breakers are useful in series combinations because, for safety purposes basically. So if something goes wrong with the whole circuit, you want to break the current in all the devices, and then the circuit breaker could be placed in series with all the resistances. So equivalent resistance. So this is a formula that can be used to calculate the equivalent resistance of two or more parallel resistances. Basically, the inverse of the equivalent resistance is equal to the sum of the inverses of the individual resistances. So if you have two resistances, R1 and R2, you have to calculate the sum of 1 over R1 and 1 over R2, and the equivalent, the inverse of the equivalent resistance, 1 over Req, would be equal to this sum. And from there you can find the magnitude of the equivalent resistance, Req. It is important to note here that the equivalent resistance is always less than the smallest resistance in the group. So this is a worked example of a complicated configuration where you have both series and parallel resistances, and 8 ohm and a 4 ohm resistances are connected in series, and a 6 ohm and 3 ohm resistances are connected in parallel, and their combinations are connected in series with the other two resistances. So you can calculate the equivalent resistance for the 8 and the 4 ohm resistances. They are in series combinations, so their equivalent resistances are given by their sum, 8 plus 4, and that comes out to be 12. And for the equivalent resistances, you can calculate using the formula we have shown, the inverse of the equivalent resistance. And so it would be just 1 over Req equals 1 over 6 plus 1 over 3. And so Req will come out as 2 ohms in this case. And then notice that the 2 ohm resistor and the 12 ohm resistor are now in series. And then you can apply the equivalent resistance formula again for series combination. And you just have to add the two resistances, 12 plus 2, and you get 14 ohms as the total equivalent resistance of this configuration. Over here, we will discuss some equipments that can be used to measure electrical properties in a circuit. So we are mostly interested in measuring currents and voltages across different components in the device. And the first instrument we are looking at, there is a galvanometer. This basically has a needle that deflects when a current flows through this. So the needle is connected with a spring, and the spring is connected to a motor. So if there is a current flowing, the motor gets activated and it rotates and exerts a force on the spring. Spring basically moves the needle. So if the current is larger, the needle moves more. So we will go into the operation of this device in more detail when we talk about motors in the section on electromagnetism. This is just to express this how this device measures the current. The symbol that is used to represent this device is a big G with two connecting wires, as shown here in this slide. Now let us look at another apparatus, an ammeter. An ammeter is a device that measures the current, and the ammeter must be connected in series with the elements that are being measured. The current must pass directly through the ammeter. So over here you see a circuit with an ammeter connected in series that can measure the current flowing through the circuit. Basically, an ideal ammeter should have zero resistance, so that it doesn't alter the current that is being measured in the circuit. And here's another device called the voltmeter. So this measures the potential difference between any two terminals, any two sections of the circuit basically. And the voltmeter has to be connected in parallel, so that the voltage drop across the voltmeter is the same as the voltage drop across the component that is being measured, because the voltage is the same in parallel. So over here you see a circuit diagram with a voltmeter connected across R2, because we are interested in measuring the voltage drop across R2. And the polarity of the voltmeter has to match up with the battery for the circuit to work. The voltmeter should have infinite resistance so that it doesn't draw much current through it. Kirchhoff's laws. This is a powerful tool to analyze currents in complicated electrical circuits. So there are actually two laws called the node law. One is the node law. This means that if you are at a particular node in a circuit, all the currents that are entering the node must equal all the currents that are exiting the load. That is, sum of all the currents that enters the load must be equal to the sum of all the currents that exit that node. And when you are analyzing problems involving circuits with different current components, this is a very powerful technique. If some of the current components are unknown, this enables you to calculate those components. And so the other law tells you that the sum of all changes in potentials or potential differences around a closed circuit is zero. So we have seen that potential difference in a series combination, the potential difference across various components is different, right? So if you go in a closed circuit along with the battery, if you traverse the full circuit in a loop, and add up all the individual potential drops across the various components, including that of the battery, then all those should add up to zero. That is, the potential drop, sum of all the potential drops across a circuit in a closed circuit is always zero. Now let us look at another electrical component that is frequently used in circuits. It is called a capacitor, and we have already looked at a simple case of capacitors when we talked about parallel plates and the electric field between these parallel plates, field lines and electric fields, in the context of field lines and electric fields. Over here you see a circuit diagram with a capacitor. It has two parallel plates, plus and minus. This is just a particular geometry. The capacitor can have other geometries as well. These plates are connected to the positive and negative terminals of a battery. When the connection is done, basically the one of the plates initially, suppose the plates were neutral, charge neutral. When they are connected to the battery over some time interval, gradually these plates charge up and assume the potential of the battery basically. So one of the plates that is connected to the positive terminal of the battery gets positively charged, the other plate becomes negatively charged. And ultimately the potential drop across this capacitor is the same as the potential drop across the terminals of the battery. So we have to define a capacitance, which is basically the ability to store charge, and this is defined as Q over V. Q is the charge in the circuit and V is the potential drop across the circuit basically. So capacitance is defined as the ratio of Q over V. And over here you see a circuit diagram with a resistor and capacitor in series and a voltmeter used to measure the voltage drop across the capacitance. Capacitance has the unit of farad. Farad is basically coulomb per volt. Capacitors can come in various geometries and they can have different magnitudes. Over here you see two examples of capacitors. One small capacitor with 1000 microfarad capacitance and a large capacitor with 1000 farad of capacitance. Capacitors can also be connected in various configurations. Over here you see a parallel configuration of capacitances. It is also possible in this case to calculate an equivalent or total capacitance, but the rules are reversed in this case. So the for the parallel configuration, we have to add up all the individual capacitances C1 plus C2 plus C3. So the total capacitance in a parallel configuration is given by just the sum of the individual capacitances. And if you have a series combination of capacitances, then to calculate the total capacitance or the equivalent capacitance, you have to use the inverse law. That is, the inverse of the total capacitance is equal to the sum of the inverses of the individual capacitances. So when you connect a capacitor to a circuit and turn the switch on, basically, the capacitor does not charge fully immediately. It takes some time to charge up. So there is a time that is associated with charging of the capacitor. It is called a time constant. It is defined as the product of the capacitance and the resistance, the load resistance of the circuit, R times C, and this is denoted as tau, the time constant. And the voltage drop across the capacitance, across the capacitor is given by this expression Vc equal to the supply voltage times 1 minus e to the power minus t over tau. T is just the time after the switch has been turned on, and tau is the time constant. What is a short circuit? A short circuit occurs when there is almost a zero resistance between 2 points at different potentials. So you have two different potentials and there is not much resistance between them. Then we know V equals IR, right? V is some finite value. Resistance is almost zero. So I has to be very large, right? So this means when there is a short circuit, there is a very large current that occurs in the circuit. And when there is a large current, it can do a lot of damage, right? So because different electrical components can only take up certain amounts of currents, and if the actual current exceeds their specifications, then the equipments could be damaged. So in a household circuit, for safety reasons, we typically use a circuit breaker. So if the current in the circuit, in the household circuit, exceeds some specific value because of some problems, then the circuit breaker will start working and it will make the circuit open so that the current cannot flow anymore. And this will prevent damage to the various electrical equipments. Also, if there is a short circuit or there is a live wire somewhere, if the person is in contact with the ground and is touching the live wire, then the person can be electrocuted. So you have to be very careful about such cases. This brings us to the topic of electrical safety. Electric shock can result in fatal burns. Electric shocks can also cause muscle contractions and failure of vital organs in the body, such as heart, for example. The degree of damage that electric shock can cause depends on a variety of factors: the magnitude of the current, the length of time the person is exposed to that current, the part of the body that is touching the live wire, for example, or the part of the body in which the current actually flows also. So that is also important. So all these factors need to be taken into account when assessing the damage done by an electric shock. And what are some of the magnitudes of currents can cause damage? So if you are exposed to 5 milliamperes or less of currents, then you can get a sensation of shock, but this is mostly harmless. It won't affect you much. But suppose you are exposed to a 10 milliampere current, then you can have some muscle contractions. Muscles can contract, and if you touch a live wire with that amount of current flowing, you may not be able to let go of the wire. What if the current amplitude is about 100 milliamps or bigger? Then if this amount of current passes through your body for 1 second, this can be almost fatal. And respiratory muscles such as lung muscles and can be paralyzed by this amount of current. And in many cases, currents of 1 ampere of magnitude can produce serious burns. Sometimes this could be fatal burns also. No contact with live wires is considered safe whenever the voltage is less than 24 volts. Power supply provided in the lab have circuit breakers to prevent possible electrocution. Most importantly, we have to be very careful about electrical safety when we are operating electrical gadgets or conducting experiments in the lab. In physics, we have to do various electrical measurements, so you have to be very careful about these safety issues so that you don't get electrocuted by accident.